Let me turn off my video so that we have more bandwidth for our. Okay. Now we're now in chapter 2. Yesterday we stopped at this equation, which is differential of P in Z equal to our specific weight, negative specific weight. Specific weight equal to rho G, and review an equation that you learn in your dynamic class. So your gauge pressure equal to absolute pressure minus your atmospheric pressure. Yeah, you take absolute minus P ATM here, right? Atmospheric pressure here. So then you get what is your gauge reading or sensor reading here. Today we're going to look at standard atmospheric. So this chart also in your handout, tutorial question number 3. This is under US standard atmosphere. The axis we have here is elevation in kilometer versus temperature in Celsius. So as you can see here that as we increase our height from sea level, you can see that our temperature is dropping from 15 Celsius, and it dropped until negative 56.5 at 11 kilometer. So if you so this is the behavior of our atmosphere, and this data was collected above US in the US. So in Asia, it will shift a little bit the line. However, it will still show the similar behavior in the line. So this is how the temperature behave. So from 11 kilometer to about 20 kilometer, you can see that the temperature remain same at 56.5 Celsius, and then it change again according to the line here. So this diagram is very straightforward, so you can refer it when you need it. Yeah. So this graph will help you if the question asks you what is the temperature at certain height. Okay. Yeah. Then there is a table that I also included in your handout. This is table 3.1. It tell you what are the standard parameter that we have. So when we talk about sea level condition, means in the question later on you see in either in your tutorial or in your test or final exam, when sea level condition, this phrase was mentioned, then we are referring to the value that you see on the screen right now. The table or the value in table 3.1 apply. So if you're having a sea level condition or standard atmospheric atmosphere condition, meaning you are looking at temperature at 15 degrees C, 15 Celsius, pressure at 101.3. So these two magic number you should always remember as long as you are doing introduction to fluid dynamics or mechanics. So density of your air will be 1.225 kilogram over meter cube. Viscosity will be 1.78 10 power negative 5 kilogram meter second Pascal dot second. So this is all the numbers that you should know where to refer to when the question mention analyze at a certain setup, a preset condition. On the right hand side, this is English value. It is only useful when for this module we will use unit SI. However, for the English, this one is useful when you work in the Europe or you work in the US. Next, we look at a few instruments that used to measure pressure. Let me check. Who's still not here? Okay. Let me know if you're not able to see the slides or you're not able to hear me. Yeah. So we look at incompressible liquid. So the first instrument we look at is manometer. And again, review or recall, every time we mention incompressible, meaning our density is constant, because you're not able to change the mass, you're not able to change the volume. So when you do the calculation for density, you get a constant value. And under a constant gravity, then you will get the equation that we covered just now. Rho P over rho Z equal to your specific gravity, specific weight. So negative rho G equal a constant value. Because your rho constant, G constant, you times these two together, you get a constant value. Now we're going to recall or call your integration skill in this section. So we want to find what is the change of pressure when we change our height. So what do? You rearrange the equation. You move your delta Z or partial Z here, delta Z to the right. Then you add in the integration sign, you will get this form. So from this equation, change to this equation. We will integrate from P0 is your reference pressure to another pressure, another point. And then when you integrate on the right hand side, you integrate from your reference point, Z0, to the position that you intended to investigate, rho G dz. So the next step will be depending on the integration mathematics scale. Okay. So if you integrate left hand side, you get P minus P0. You integrate right hand side, you get and you pull the rho and G because constant value, pull to the outside, you will get Z minus Z0. Yeah. This is just a rearrange because we hate to see negative sign in our calculation, and also to avoid calculation mistakes or error. So when you integrate, remember to carry your negative sign, and you'll get Z minus Z0. And when you times carry your negative sign into the product, so you can rewrite the equation to become Z0 minus Z. Okay. Okay. The next one, if you look at this equation, P minus P0 equal to rho G Z0 minus Z. And again, in this case, is all our Z direction going up is positive. Just as a rule of thumb, when you check your pressure, how you know when it's positive, when it's negative pressure, it depends on the height that you measure. Okay, so yeah, it's just a mathematics notation. Z0 minus Z, you get your H. Okay. So the equation above, the change of pressure, P minus P0 equal rho GH. This is what you learn in your dynamic class, right? So change of pressure equal to rho GH. And this equation, change of pressure equal to rho GH, was used for a device called manometer. Okay? A manometer is used to measure pressure difference between 2 points in a static incompressible fluid. Yeah. So manometer, we measure 2 points in a static incompressible fluid. And if you look at the diagram here, if your Z going down, the pressure will increase. Just a rule of thumb. So every time you go down from a reference point, your pressure will increase. Okay. And if you going up, the pressure will decrease. So that's rule of thumb, yeah. So remember, every time you go down, pressure will increase. You go up, pressure will decrease. Go down, positive. Go up, negative. How you remember this one? You imagine you go underwater. So the deeper you go underwater, the more pressure you'll experience because more water will press on your body. So if you go above water, you go into the air, the higher you go, the less pressure you experience because less air molecule will press on your body. Okay, so this is how you memorize it. We'll look at one example with this manometer, and this one can be found in your tutorial handout, question 7. So a normal blood pressure from a human is 120/80 mercury height, mercury. By modeling a manometer as a U-tube manometer here, convert this pressure, this mercury pressure into PSI G, or pound per square inch gauge. G is gauge. Yeah? So you pump in your blood pressure from the left. So the blood pressure will compress the mercury inside the U-tube here. And you can measure the difference of height from this point to this point, given by H here. Okay. So in any standard procedure, we will look for information given. So the information given is pressure in mercury. One is 120 mm, one is 80 mm. And then we need to find pressure in PSI, pound per inch, pound per square inch. So we apply the hydrostatic equation that we learned just now. Delta P equal to rho GH. Okay, this one. So in exam, if you write this correct equation for that particular question, you will get free 1 mark there. Okay, so in exam, as long as you write equation, the correct equation, you will get some point as an evidence of your understanding. Now we assume that we are having a static fluid, incompressible fluid are using, and we ignore the air density effect. Yeah? Okay, we continue to solve. First step is you look at this point A here. I start to use my pen. Here, pressure at this point and pressure at this point, because these two are exposed to atmospheric, so your pressure gauge reading at this surface here will be 0. Yeah? 0 gauge means your P gauge will be 0. And you can write. You draw a line every time you do calculation for fluid pressure in a tube. You draw a reference line from the beginning and the end. So you draw a line. You in the screen here, you will see that you are having A and A prime. A prime is the same location as the same horizon as A, and then B is location B. So how you convert the information into the governing equation. Pressure at A will be PB, pressure at point B, plus the pressure created by the mercury above A prime point. So we can write plus rho, and in this case, be careful, we are using mercury. So rho mercury GH. And just now, because point B exposed to atmospheric, so PB equal to 0. This is a very powerful statement. It will help you to simplify your calculation in future. As long as the surface exposed to atmospheric, all the pressure measurement at that particular point will be 0. Okay. So no matter how complex the system that we will give you, if this point and this point exposed to atmospheric, P1 equals 0, P2 equals 0, as long as exposed to atmospheric. Okay. Okay, cool is here for the record. Okay, we continue with the calculation. So you have pressure, the experience at point prime A prime here will be equal to rho GH, and the rho here depends on the liquid itself. In this case, the fluid is mercury, so you use mercury density. You change the density of the mercury by using Sg times the water density. Recall this service specific Sg definition is rho divided by rho water. Okay. So again, if you write this equation in your answer, you will get 1 mark also. So there are 2 free marks inside this portion. You substitute the answer, right? Then you get the pressure at A. Just a quiz, or just a short question, ponder to think about. What happens if, let's say you are staying in A prime point? What happened to the pressure if you go down from point A? What do you think the pressure will be? The pressure will be increased, or the pressure will decrease?
Increase.
Increase, huh? Correct.
Yeah.
So anyone don't understand why increase? Anyone? You don't understand why it will be increased? Okay, yeah. So the pressure will increase as you go down. And what happens if you go up from this point to point A here? The pressure will
Decrease.
decrease, correct. So this is a very important concept. Huh? So same, huh? When you go down, when you go up, pressure will decrease. Huh?
Please.
Yeah. And the value, yeah, okay. So straight away, we go to the next slides. Pressure at here will same at pressure at here. Okay. Pressure at A will be pressure at A prime will be the same. Okay. This is an important concept. If you study about manometer, this point will same as this point. So PA prime equal to PA here will be Sg rho water GH. Because we are going to measure the blood pressure here. Okay, our blood pressure is 120/80 mercury. So how do we continue from here? So again, refer to Appendix 1, Table A1, Appendix A, Table A1. You're going to find the mercury equal to Sg equal to 13.6, water is 1.94 slug over feet, because the question asks you to put in unit English unit. Yeah, so if the question asks you to change in Pascal, I think you should be able to do it also. Yeah, just a unit conversion. So you do the calculation. This is just a expansion of the detailed calculation. Okay, so you just plug in all the numbers. Rho Sg equal to 13.6. Raw water, according to table or Appendix A1, is 19.4 slug per feet, and you change accordingly to psi pound square. So this one we already show you in the previous lecture, how you convert all this. At the end, you will get your P at a height of 120 mercury height mm, or in medical term, they call it systolic pressure. So systolic pressure equal to so and so, okay, equal to so and so, equal to 2.32 psi. All right. So what is important thing that we need to remember here is that the definition of Sg, the definition of the pressure at a certain point. So what happens if you go down? What happens if you go up at a certain point? And the pressure at 2 points will be equivalent. For in this case, point A, pressure at point A will be equal to A prime, pressure at A prime here. Okay, I leave the detail here on the slides. Later you can come back. Another one is on the 18 mm mercury. And medical term for 80 mm mercury, they call it diastolic. So again, you change the H value inside the calculation, because your equation is PA equal to SG rho GH. So just now your H is 120. Now you do the second one, which is 80 mm mercury. So you change the 80 mm mercury in the unit that requested by the question. You do the calculation, you'll get 1.55 psi. But all this value is just a reference. Important that you understand the principle behind, the reason behind all these steps. Any question for this question? For this tutorial question number 7?
No.
Okay, we look at another example. This one is in your question number 8 tutorial. So let's say you have an inclined tube. Yeah, it is what you see on the screen here. The question asks you to derive an equation using what you see on the screen here and what you learned previously. So you have a container with a diameter of D, and then you have a tube here that fill in with a liquid. The liquid is unknown, but you can define in a universal equation. And the tube is inclined with a angle of theta. The L here is the reference line from the meniscus of your liquid. Yeah, from L to the exposed here. And the diameter of this one is this one. Okay, just a quick check. Since Ku, you checked in a bit late, I'm going to ask you a question. So Ku, what is the pressure at this point? If this exposed to atmospheric, what is the pressure at this point? What is the pressure at this point? I name as X maybe. What is the value at this point? If this one exposed to atmospheric. Ku, what is your answer? Ku, are you there?
Yeah.
Yeah, what is the answer for the question I just showed you just now? The slides on the screen here. What is the value at that particular point? I label as X. What is the pressure at this point? X. What is the gauge pressure? What is the gauge reading at X there?
SG, right?
Yeah, what is your gauge reading? Or what is the
What is
pressure
it?
reading at that point? The hint is exposed to atmospheric pressure. I'm asking you about the gauge. Don't give me the atmospheric pressure value. I ask you the gauge pressure. What do you get from your reading? If you install a sensor there, what is the reading that you get at point X?
I don't get it.
Okay, Oliver, help Ku to answer this one. What is the gauge reading at location X? Oliver, are you there?
Yes, Sonia.
Yeah, what is the gauge reading? If you install a sensor at position X, what is the reading that you will get on your sensor?
I'm not too sure.
You're not too sure. Are you in the classes now?
Yeah, I was.
Okay. Amir, you want to Amir, you want to help? What is the gauge pressure at position X?
So this is not the atmospheric pressure, yeah?
Nope.
Okay. Not sure, sir.
You're also not sure.
Yeah.
Oh man. You want me to repeat one more time?
Yeah.
You can read from the start, right?
Yeah.
Yes. Yes, sir.
What is the reading on B here from the slide?
ATM, and therefore 0 get.
Okay.
Just now I mentioned if the fluid surface exposed to atmospheric, what is the reading at here? P gauge.
Okay.
Equal to what?
0.
So the same concept. I just apply what I mentioned just now. I ask you, what is the gauge pressure at here? This
0.
small explosive.
0, 0.
Okay, good.
Okay.
Give you hints already. This kind of question will come out in tests, and it's a free question, a free mark question. I will just give you, for example, section A. Calculate the pressure at a certain point. For example, let's say I give you this diagram. Calculate the gauge pressure at X position. And it might be 2 to 3 marks. I put it there, explain. So if you're not able to answer, you are missing the 2 to 3 marks, 3 marks there. Okay, so I'm helping you to score some marks at the moment. Please remember, this is a very important concept because after this, when you go into deeper in EE 3279, with this fluid mechanics module, all this will not be mentioned anymore, and we assume you already know. Okay, so it's an important concept. Okay, now we continue to solve. So we need to express our L in terms of delta P, and we apply equilibrium for our reference. Again, we are using the equation that we learned today, the only equation we learned today. Delta P equal to rho GH, and SG equal to rho divided by rho water. And we assume that we have a static fluid and incompressible fluid there. So we label point 1, point 2, and in the diagram that the dotted line is an equivalent liquid level. It means pressure at this point will same at pressure at this point. Okay. The first parameter you need to input from the free body diagram will be the distance between the equilibrium liquid level to the surface number 1, labeled as H1. So this H1 will give you some idea on the pressure created that push the liquid down to a certain height of H1. Second parameter we focus on is from the equilibrium liquid level to the position number 2, we label as H2. So we apply the governing equation, delta P equal to rho GH. So how we calculate differences from point 1 and 2? We take P1 minus P2. P1 minus P2 will equal to rho GH. The total height that we are focusing on is H1 plus H2. Is a total height of the liquid from the this is the total height delta H of the liquid. Understand?
Yes, sir.
Okay, good. Then a side calculation. to eliminate, the next step is that we're trying to eliminate the H1 term in the equation. So we try to change, we use the concept of volume to change it so that when we do calculation later on, we can eliminate the H1 term there. We use volume. So volume, how you calculate volume in this height? You take, because this is a cylinder with a diameter, you take pi r squared or pi d squared divided by 4 times the h, you get the volume of this space here. It will be equal to the volume inside this inclined tube. So how you find volume in the inclined tube? You take the area of this tube, which is pi d squared divided by 4 times the length, you get the same volume. What you press in will come out from here. So your space here will equal to the volume here in the space here will be equal to the volume in this arm. You rearrange the equation in H1 term because we want to eliminate the equation. We want to eliminate H1 in the equation. So after you rearrange H1 equal to D divided by D2 square H, you substitute this equation into the governing equation here. And what else? Okay. Then we also want to eliminate our H2 in terms of L. So from here, how to calculate your L? Use trigonometry equation. Your H2 equal to L sine theta. Any one of you don't understand how to get L sine theta?
No, sir, it's okay.
Cool, you
Yeah,
understand?
fine.
Cool, you okay?
No understand.
You don't understand?
Yeah.
Okay. You focus on this arm. You are seeing this is your L. This is your H2. You have a theta. What is the relationship in trigonometry? What is the relationship with the opposite arm and the hypotenuse? Cool.
Cos. Sine, right?
Okay, it's a sine theta equal opposite divided by hypotenuse. You want to eliminate H2, so H2 equal to L sine theta. Do you see it now, cool?
Yeah.
Okay, so
Okay.
yeah. So now you substitute your H1 and H2 inside the governing equation. So now your equation don't have H1 and H2, you only see L and D and capital D in this form. Okay, you substitute inside there, you get in this form. So your delta P equal to rho of the liquid. There's a small sub L here represent the liquid. Rho G H. So your H is a combination of H1 and H2. Okay. So we're getting more and more complex system here. Make sure you understand how to get your total H here. Okay. The next step is just tidy up the mathematics equation where you pull the same factor L go outside. Then in your equation, you only have inside the bracket, you only have D d divided by capital D square plus sine theta term. What else? And the question asks us to put in the term of L, right? If you look at the question asks you to put in the expression of a liquid deflection L. So you rearrange this equation again to put L in one side and other parameter in one side. So this is the answer for question number 8.
So, sir, I just need to put it in an equation, yeah?
Put it in what?
In a form of equation, yeah?
Yeah, correct.
Okay.
Yeah. So and then another one is let me see. Okay, another one is to find the sensitivity of the manometer given by this equation. Sensitivity of manometer given by L divided by H. L is the arm. H is the height of the parameter of the measurement. H divided by L and H. And yeah, H equal to, because delta P equal to rho GH. So you rewrite the equation, you'll get this equation. Because the L just now is what you define. Your L equal to delta P over rho G and the term here, D divided by D plus sine theta. You just substitute back into this equation. Okay. And you use this H equal to delta P over rho G. Okay, this one. Substitute here. This one. Substitute here. You do your mathematical cancellation. At the end, you get this answer. Okay. Now, important part is sensitivity. This is the second equation you learned today. Sensitivity of barometer given by S equal to L divided by H. Any question for tutorial question number 8?
No, so far.
Noah?
No, no,
Okay,
no.
back to the previous question I'm going to ask. Cool. What is the gauge pressure at point number 2? What is the reading at
0.
point number 2? Okay,
0.
good. Correct. Okay. All right, we go for a short break. Let me stop the recording.